some of my background. I also started a startup before, Ubook. We developed a curriculum and an app to teach kids how to code. It's currently in around 30 countries. And I stay there as an advisor. I don't have any more that amount of time to dedicate, but at some point during around 6 years, I was pretty much full-time working with Ubook. So I forgot to mention that. So for that, so if you're able to follow me, all right, somebody, okay, so Ella already voted. I can actually hide here the results so everybody can vote. So this is the screen I'm talking about. If you go to the, I think it's the third screen, or if you click here on my face to follow me, you should be able to see the screen and just vote however you feel like it. You don't have to actually vote now. We can move on, and I'll just start the presentation because we have a lot to cover for today, right? So feel free to come back here and just share with me how familiar you are with AI. I would be very interested in that. So the first question is, I guess, something that is, well, self-explanatory, I think, for most people here, I'm sure. However, actually, eventually I get this question a lot for why is it relevant now? Why wasn't it not as relevant before, or etc. I guess it became really more relevant, or at least famous, the concept of the term AI in recent years, for obvious reasons. But it's not a recent term. It is actually a pretty old idea, and I'm going to go through how can we just really arrive to this, and what are really the basics on this. So I'm just going to start by even a more fundamental question, which is, what is a computer, right? So what is it for? And at least it is an activity that's been recorded in history for 5,000 years, probably. So these are like the first abacus, like a reconstructed abacus from I believe, Samaria. So this is a computer in a sense. It's an arithmetic computer, but it's quite capable of doing many things. So there's sum, subtraction, and sums. You can actually do multiplications with it as well. It is not really good for divisions, but you can also do it. There's all sorts of techniques you can use to process large numbers on this, and using abacuses with fingers and with other objects. There's all sorts of techniques to actually make this a pretty general machine. But it's an old activity, so computers have been really old, and I found it interesting to use this idea of starting to think about the computer first before we talk about AI, because in the sense it is nascent in the idea of what a computer is, and there have been attempts to create more capable and more general, let's say, computational devices. Let's not say they would be the concept or the modern idea of what a computer is, which is more of a general purpose computing machine, right? These computers in the past were very narrow. So you saw, an abacus is mainly an arithmetic computer. The Antikythera mechanism here is a planetary movement predictor computer. It's pretty much an algorithm in solid form. You'd also have, let's say, fake computers in the past, right? The mechanical Turk illusion, which was a computer in disguise. Actually, a human would be actually controlling this machine that would be playing chess with somebody else. But the ideas were already here, right? So this would be around, the 16th, 17th century, the first few, ideas from what a mechanical Turk was. It became quite famous in the 18th, 19th century as well. But ideas of making machines that actually work by themselves and can actually process and comprehend the world was here before, right? Of course, before all these illusions and or these narrow computers, none of the modern era was possible. And the first, let's say, proof of concept of what a computer was really, or a general purpose computer was this analytical machine made by Charles Babbage. This mechanical thing. It was not electronic as computers are today. All of the logic system was basically stored in a couple of wheels here that would rotate and proceed with logic. And this is actually the first program written for that computer. So this lady here, this woman here, was actually the first programmer in the world that wrote an application to be run on Charles Babbage computer. And although it's very neatly written, it would actually need to be mechanically programmed. So the computer would actually, all these wheels would actually need to be reconfigured manually for it to work, right? So we're quite far from that idea, right? And mainly because of thinkers such as John von Neumann and Alan Turing, that the modern idea of this electronic system that we today call a computer became possible, right? In the beginning, it was not a completely, let's say, it was an electric machine that used vacuum tubes to actually do the logic integration, but eventually it became just logic switches, and eventually the transistor came about and revolutionized what we can actually do about with logic, right? So, but the concept is always the same. Is always the idea of making a more and more capable, more and more general logic system that could actually process anything, right? Anything we could think about, this machine could be able to process, right? So I'm just really going fast on this because this is really just an intro here, but this I would say is really one of the key components of at least the thesis that I'm trying to bring about why AI actually became meaningful today, and why not 20 years ago if these ideas already existed. And we're going to see that some of the core ideas of for modern AI, even transformers and etc., really existed before. And it's mainly to do with this capability, right? So the humanity's capability of just stuffing more and more transistors into a smaller and smaller area is really the key here, right? These abstractions for how to make more and more complex algorithms would actually require a lot of logic built in, and that is not possible to process if you don't have trillions of transistors in a machine. And this is here is, I have to say, and to emphasize, this is a logarithmic vertical axis. So things are going at every large, line, they're going 10 times as before, right? So this curve would actually be sort of exponential. Some people say we're reaching the end of the capability, right? We're reaching the atomic level where quantum effects make this impossible to actually make it smaller. But already designs on how to improve this and how to change the architecture in other dimensions, etc. But at least this is a core element here, right? So computers became more and more capable because the amount of transistors they actually had, right? So just what is a computer? And I'm going to just keep using our friend ChatGPD to help us answer some questions here. So a computer is a programmable device that processes data and performs tasks based on instructions, featuring mechanisms for input, output, and storage. So actually, this last sentence that it included here is something that comes from the Turing theory, right, of a Turing machine, that there's a separate idea for input, output, and storage. But basically all computers today use this, right? So might as well just include it here. And also it can process data and perform tasks, right? So we kind of agree with this in general terms. I guess it was a much longer sentence from ChatGPT, but try to compress it as much as I could. Now, how can we go from computer to AI, right? How can we go from this idea of a machine that just processes programs, let's say, from an input, output, and storage configuration, and performs tasks based on instructions? How can you go from that to an actual intelligent thing? And it's not an easy question here. It comes from philosophy, right? So there's plenty of philosophical development in the past that kind of got us to here, right? So from the dualism and materialism ideas that basically said that the mind can actually be mechanical in its way, or can be explained mechanically, right, from Descartes, or even that materialism, that the brain would be the machinery that makes possible thinking. So in a sense, these core ideas are very important here, because it kind of started to approach the idea of that intelligence could actually be explainable through the laws of nature. But it would be until perhaps this time around, and the 20th century, where ideas around robotics and artificial thinking machines really just started to become popular. And this is the coining of the word robot as well. So Rohr, or Rossum's Universal Robot, is a play, a Czech play, that would be basically popularizing the idea that you could make a thinking machine. So you could actually make a robot that would have its own ideas, and eventually they actually do exactly what robots even do in our movies today, and they become self-aware and kind of revolutionize and go about and destroy mankind in this place. So this was quite ahead of its time, and let's say the robot's tale has not been rewritten ever since. It's been just pretty much following the same structure from the beginning. But it was not until perhaps this famous publication by Alan Turing, the most famous one in artificial intelligence, that the idea that you could actually make a thinking machine reached, let's say, a scientific, credible discussion. And it's quite curious because this publication is actually on psychology and philosophy. So the first quote here, Computing, Machinery, and Intelligence from Alan M. Turing, is a publication in a psychology and philosophy journal. Is not on a, let's say, engineering or scientific, let's say, more general mathematical scientific journal, but one more philosophical, right? Which is quite interesting. And following that publication, of course, many people just started coming into these ideas as time passed. A lot bringing about what Turing started, and actually at this time starting to describe how could we make these thinking machines, and how could we actually make machines that would learn, that would be able to understand the world from complexity and not just by numeric input. And these three are kind of like, let's say, the forefathers, and you probably recognize them because you're still quite famous and work in companies such as Google and Meta today. These publications from these guys were actually mostly theoretical at the time. They were algorithmic explanations of what you could, how could you actually build thinking numerical systems. But during the 80s, computational power was still not quite there yet. Although you started, playing with the idea of neural networks back then, in a physical sense almost. And we're going to go a little bit, now into what is this idea of what a neural network is, and why is it meaningful for AI. Right. So going back to our friend here, ChatGPT is asking, helps us a little bit answer what AI is, at least to its own definition. It is a field in computer science that strives to create systems that are capable of performing tasks that require intelligence. So I found this one very interesting, and I tried a couple of times, and it's not that different from, of course, the Wikipedia version of it. But it is not a finite explanation, right? So to understand artificial intelligence, by definition, you need to understand what intelligence is, right? Because in a sense, artificial intelligence is nothing more than an adjectivized name or noun of intelligence, right? It's something that says not natural intelligence, right? So we need to understand what actually this means. And actually, this is one of the most complicated questions here. And I'm not going to go too deep into it at all, but it is one of the questions that stays on by the term. And perhaps one of the points that I would like to also make more here, which is that this term, because the definition of intelligence changes, also changes, right? As we understand more, or at least are able to explain in a more organized way what do we think about intelligence, the term artificial intelligence follows, and vice versa, right? So artificial intelligence also influences our concept of what intelligence is. So this is a shifting term, right? But let's just begin with what we understand today and what the theory of, let's say, neural networks is based on, at least in a theoretical sense. So on our left here, we have a representation, a graphical representation of a neuron. This is the cell that, as you know, the cell that makes up brains and neural pathways in our bodies and heads, but also of animals and all sorts of creatures. It's quite complex. It has all these ramifications. It has a core, right? It has this little cellular body, and has mainly two types of ramifications. One very long, called the axion, and then a couple of other ones, which are dendrites or rasiomes. They just basically form connections with whatever other elements are here, and the axiom as well. They have two different functions though. And we're going to just represent the neuron as a little dot, as basically, of course, we're not going to be needing to just model complexity now. Let's start simple. So we just add another neuron into the mix. And what we do now is we try to represent what neurons actually do in nature in a mathematical way. So neurons are signal processors, in a sense, that connect with impulses. They receive an initial signal, let's say, they set it to the next one, and the next one is tuned, has a bias to respond to that signal, to a specific value, right? So it's going to respond to a value, but not to others. And it makes it so that in the very essence, in a very simple way, each neuron here is a tuner, right? So we can tune it to, let's simplify, to a value, a floating value between 0 and 1. We tune the other one to another floating value. We tune the other one to another floating value, and they're gonna process. They're gonna do some mathematics inside of them. They're gonna change the values, and in a very basic way, this is just what they do. So it seems quite a dumb, simple thing that has no intelligence by itself, right? And in fact, when we just have a couple of neurons like this, these systems are not that intelligent. They're as smart as a relay for radio, right? So they're quite dumb. It is not the simple neuron that is intelligent. It is the connection between hundreds, thousands, millions of neurons that actually makes all these combinations of all these weights and biases. The connections have weights and biases here that tune the pattern in a way that it is capable of performing amazing tasks collectively, right? It's an emergent property. And we did actually need to start to see this happening in nature. So it came from biomimicry. As you can see here, it's our I think this is the hypothalamus here. So this is kind of like our Rockidian area, and there's the bulbus here. There's like the neocortex around it. It's kind of like the slice of our brain, and we can see the different neurons being excited, right? Visually, it's kind of a mess here, hard to explain. But in a sense, it is doing exactly a similar thing to what we see here, but in a very large scale. So what can we do with these neural networks, right? We can apparently teach them how to, do stuff, things that are actually working on the real world. And this is an image from a video that I really recommend to anybody to follow up from, and I'll share with you guys from a 3 Blue and Brown. It's one of the best videos that popularized the explanation from how can we think about neural networks in YouTube. It's really the best visual explanation I've ever seen. And you can see here that we are in the end representing an image, right, of this number 9 here with little pixels, and each one of the pixels has a value between 0, black, and 1, white. But when we break down each one of the values of pixels into actually just a line of continuous values, and we encode that line to the first neural layer here, right? This is the first neural layer. We actually doing exactly what our brains do, right? Our brains bring in image from the world. This image reaches our retinas. Our retinas process data in different process light in different quantities, and these quantities excite the neurons. They're going to be exciting neurons differently, though. So some neurons are going to be excited with certain values, and other with others. So the trick here, as you can imagine, is how can we determine what are the values we should tune these neurons to be excited for? So in its most difficult part of this type of science has been how to actually reinforce the learning, how to actually implement learning here. And there's many ways of doing this. There are simple ways from backpropagation to all the way to genetic algorithms. There's all sorts of ways. Today is quite available, a series of these type of learning mechanisms. But in essence, what is done is a brute force kind of approach where different neurons are tuned in initially in sort of an almost randomized way. The data flows through it, and in the end of the neural network, there's a goal that educates if different neurons reach that goal or not, right? So if, for instance, the end goal is to detect the number 9 and the neurons are detecting number 3, that's a bad configuration, and the brain tries again and again until it starts reaching a stronger connection with the ideal value. So it's in a simple format. This is it. So I'm just going to give you an explanation or an example of this type of thing working in real time, and how can you actually already do this type of visual-based neural networks called CNNs in real time, even working on our browser without requiring any big computer. So it's quite a democratized technology. I'm going to skip that tutorial. So I'm just going to train this. If you're seeing my screen right now.
Yes, we can.
Right. So this is one of the best, I would say, toy explanations of a neural network being used in real time. It's made by Google. There's already new versions of it. I think it's quite useful even to teach kids how to do this. We use this a lot on Ubook as well. So what I'm going to do is I'm going to take samples of a source of data here, which is going to be myself. And I'm going to say that's going to be João here. And I'm just going to train this in a couple of variations, right? So it kind of recognizes my face from different angles, almost complete ones, non-complete ones, right? So, right. So now it's knowing that it's the green one. But the problem is, if I remove my face, nothing happens, right? So it just keeps detecting green. That's because it's a whole world. So the neural network only understands one source of data, which is pretty much all the same. So there's no differential source, right? I'm going to do one thing now, of course, which is I'm going to just train the image without myself. Just a couple of variations. They don't need to be many. And now I can detect my face, and when my face isn't there. So of course, this neural network is quite dumb. It doesn't know. Perhaps if it would see another human face, it would say, that's João. But see how easy it is in the sense to actually make this happen, right? We just took actually a couple of examples, and immediately the neural network works just by getting a different data source. If I'm going to make a harder one, so I'm just going to make like my hand here. So maybe give them more examples here. So now hand, might be a hand, might be a face, right? Sometimes it's not really clear. And now hand and face. It says face is stronger, but so basic. This is a basic example of what we can actually do here, right? So in the sense, as you can see, there's an important part which is the data, right? So the amount of data we have and the types of data are going to dictate how good, how well these neural networks perform, right? And I just took a couple of hundred images. That's very little, right? These very powerful CNNs are these days that run on self-driving cars. They actually are trained in trillions of categorized images that basically follow the same process that I just showed you. So yeah, so neural networks are everywhere, right? They do everything these days. Basically, they run all sorts of image detection algorithms, but not only. They also do voice detection. They also classify trends. They also are used for general mathematics, but also for all sorts of self-driving and flying vehicles, from drones to visual systems for robots and cars. Even the tuning of the flight controllers from SpaceX are using, or at least at part of the process, they do use the neural networks, although they don't fly the neural networks themselves. But they're pretty much everywhere. Right, so finalizing our little trip here for the intelligence question. Well, I do like this one, which is using knowledge to manipulate one's environment. There's all sorts of classifications, and I'm not saying there's one that's better than the other. I'm sure each one of us here would have a different definition of what intelligence is. There's all sorts of good, smart people thinking about this as well that have all sorts of definitions. But I'm going to go with this one for using knowledge to manipulate one's environment, because I think this one is a useful one, right? So far, computers would not really be able to manipulate the environment. They would be able to follow instructions in a blind sense. But now computers are able to actually change things around. They're able to change. Well, they're starting to change the web, right, in real time, and eventually they're going to be changing the world as well. So yeah, so these are the kind of two steps, right? Before we had these, neatly simple, some very stupid little program that just randomizes a connection to different definitions for intelligence and just runs them and runs a random one. And up to computers actually know things. Apparently, they understand things. Algorithms that know the difference between in the word jump or walk, right? Which is not written anywhere. There's not a place where it's written, which is quite weird. And I'm going to explain a little bit how that's done. So yeah, so this was last year, right? So OpenAI in 2022 November launched ChatGPT 3. Immediately after, things quite heated up a lot, right? So OpenAI's ChatGPT was the fastest growing ever continuously operating platform. I do think that Threads from Instagram was had a faster rate of adoption. Although, to be fair, the rate of adoption was kind of forced, and so I'm not going to be able, and it was already built on top of Instagram. So I'm not equating both, and I do think that Threads is not really, I wouldn't say it is as popular or as successful as what the effect of ChatGPT or any other of these platforms actually done in the world. But that's just me. So yeah, so basically in 60 days, over 100 million people were using ChatGPT last year. The trends are, they're changing, of course, because there are now many other LLMs in the world that are quite good, and even some of them even competing to be better than ChatGPT or the GPT system. But it was quite interesting how fast the adoption rate was. So this was quite an explosion, never seen before. And yeah, this is kind of where it is, right? So ChatGPT basically at the time showed this series of charts comparing how the system would be able to perform on different exams done by humans, from just AP environmental science, art and history, all the way to calculus, and all sorts of other applications from chemistry, etc. Which in 3.5, the previous version, was quite not that good, but ever since they launched GPT-4 and GPT-4 with Vision, and now the 4.0 system, they're even better, right? So these systems are getting incredibly good at reasoning. So the core product here was really this ability to reason, apparently. But it's quite strange, right? I mean, now I'm going to explain why it is strange to think about that this system is actually reasoning. But before that, just the state of the art. As you know, all the big incumbents tried to compete directly with OpenAI. Two of them actually joined forces with OpenAI and opened a couple of legal problems there, right? Which was Microsoft and Apple. More recently, Apple, right? The most recent one of these. But I would say that the actual ecosystem is the interesting part. So OpenAI still, in a way, dictates the trends. So they are the early releasers of capabilities in a sense. Although there's a couple of different players here that really are starting to become very strong and interesting competitors. There's many more. I mean, I'm not even putting here Mistral here, or from Mistral, or a couple of the Chinese incumbents or up and coming startups as well. But a notable two mentions are at least this guy here, so Claude from Anthropic, and Llama 3 from Meta, which is, I would say, the most impactful LLM in the world economy, since it's open source. It's actually something that was built by hundreds of thousands of people actually took part in the work of Llama 3, which is the third free open version of Meta's LLM. And Claude 3.5, which is apparently quite capable, although it's edge to edge with OpenAI. And I'm going to show you what a bit of the capabilities are there. So yeah, we live in this continuous wave of more and more products that say that use AI. AI has become sort of an empty term almost, right? Since it means more and more things. And when we use words that just mean too many things, they just start becoming a little bit useless. But I'm just going to try to break it apart, what we actually mean by the modern AI stack. And this is going to be in the perspective of the trends that most people are adopting, and it's not involving everything. So as we saw before, you saw like SpaceX landing. That's not really what we say, when we mean AI these days. In the past, we would call that AI, but those are control algorithms. Even how we do self-driving cars these days, you can call them AI, of course, but they're not doing at all what the LLMs are doing. They're doing something very different. They're also using machine learning. They're also doing reinforcement learning. They're also using neural networks. And there's definitely a zoo of different neural networks. There's tens or maybe even hundreds of variations of architectures. But we're going to focus a little bit more today on the LLMs, which was all the time I had. But there's definitely more variations that are quite interesting, especially the ones that are about computer vision. So I'm going to be talking about this kind of stack here. It starts with the hardware. There's a couple of new trends on neuromorphism. So hardware that mimics, or at least does what the neural networks do directly, the LLMs do directly. Then there's the LLMs themselves, a stack by itself, right? A class by itself, developers of LLMs. Then you have different techniques of changing and manipulating the LLMs. The main two ones are the RAG system and fine-tuning. And finally, there's the layer of tools, which are mainly responsible for all these applications. Most of these companies saying that they use LLMs are companies that are actually developing tools for LLMs to use. So they're not really working on LLMs themselves. They're making tools that LLMs can use, just like how people made apps for the App Store, right? So let's start with the trends on hardware, just to stay a little bit in the lane. So to begin, there was a huge, not just because of the AI push, of course, there were previous pushes from crypto, but NVIDIA was definitely one of the prime movers here in the general adoption or democratization of the access to transformer models across the world, mainly because of their GPUs. This is a H100. It's the top of class, let's say, mostly widely used in the world. But these systems are GPUs, right? So they're using an abstraction, which works really well, but they're not using the hardware directly as a tensor. There are TPUs as well. Here you can call them as TPU as well, which is a tensor process unit, which is a name that Google coined because they didn't want to call them GPUs in a sense. But they're built on the idea that you can process, let's say, data or programs with a CPU generally, but for certain applications, some narrow applications, it makes sense to create a different type of computer that is a bit more narrow, but has some baked-in qualities. For instance, GPU stands for actually graphic processing unit, right? And it's doing a lot of graphical stuff. So it has algorithms for shaders and for graphical processing. But apparently, we can parallelize a lot more with those type of hardware architectures, and that means that we can actually use, to the best extent, these type of neural networks, which are really parallelizable. So they're much more efficient if we run an AI, a neural network, in a GPU than on a CPU. But they're not the best, and there are better systems that could actually run. And the trend here, as before, was going from CPU to GPU, right? So being a bit more narrow. So going back from the idea of making it more general. The CPU is still more general, right? GPUs are more narrow. They're less capable of doing different things, but they're better at doing specific things that AI needs. And if we even go further, this is kind of the next step, right? It's a neuromorphism. It's basically etching into the CPU structure, or at least into the processing structure, the form or the shape of the transformer model. These guys are doing exactly that. They're doing basically the hardware for LLMs and transformers. And they are, immensely more capable than an H100 or B200 does, right? So it's actually comparing 8100 here, working on tokenization. So this is the process of generating tokens that LLMs go through. And you can see here that their version claims to be much better. And it makes sense, right? It makes sense because it is a more specialized GPU, or at least CPU here, let's say. The only catch is that this type of machine is really bad at doing anything else than a transformer, right? But the world is crazy about transformers these days, and that trend seems to just be going up. So they're betting, right? This is like kind of their casino run. They're saying, okay, we're going to just go all in on transformers, and we're going to try to make the hardware for that. Okay, but regardless of this trend in hardware, what are the LLMs actually doing right now? It is quite hard. It's quite hard to know how well LLMs perform, how well they do certain things in general. That's because LLMs do not process things, let's say, in a deterministic way. They don't produce the same result all the time, as you know, and anybody here that tried GPT answering the same question more than once knows it answers a different question with a different answer every time, even if the question is exactly the same. That's because they are stochastic, they're non-deterministic. They're doing activity that is so complex. There's so many parameters in these brains, so many weights and biases and different values for them, that it's hard to actually predict what they do. So people came up with these benchmarks. And there's all sorts of benchmarks, some more credible, some less, which in essence are, a battery of questions that you can ask to transformers and LLMs, or even activities that you can make them do, and then they're evaluated. They're evaluated by humans. Some of them can actually be evaluated by machines, but well, these are what benchmarks are. So as you can see, of course, they can seem very reliable because people put numbers on them, but in the end, most of these are actually human rated, which makes them, well, biased at least, right? So for instance, we kind of look here and we see that GPT-4o is quite a good rate compared to all of the other LLMs and different of these benchmarks. But at the same time, when they did this evaluation for text generation, it was a new kid on the block. And what we saw so far as well is that benchmarks tend to go up when new LLMs are added into the pile, because people are apparently excited, and the testers are surprised with the new capabilities of that transformer model. But these benchmarks actually tend to go down as we move forward, because people get used to those capabilities. Still, there's two kids on the block, let's say right now, which are quite interesting, right? We're talking about GPT-4o and Claude 3.5, which I would say is more interesting because of the environment that they have. And I'm going to just go show you in a little bit. But in a very simple structure, I'm just going to show what I think is the thesis right now. On the left, we see that there are tools that people already use. One of these are the famous RAG tool, which is short for Retrieval Augmented Generation. So this tool here is basically doing it's giving a way for AIs to access information that's not been executed in the training of the neural network. So they can access external data. They can access, for instance, really fast and really well an enormous amount of information if we do it through RAG. It's kind of like a way of making a small little search engine, a small little Google. And in many ways, it outperforms Google search when we are good at encoding the data there. So if we want to make the LLM or the GPT-4 or Claude or whoever model we want access information that it wasn't trained on, we can actually go and give it a RAG tool. There's also other methods like fine tuning, but we're going to go there in a little bit. Then there's the coding environments, which are quite strong as well right now. So the ability that LLMs have now to run code and make that code actually give them information of the environment and change the environment with that code. That's something that I'm going to show you as well. And what I think is the next step, which already has been proven by GPT-4o Mini, is streaming. So far we've been looking at LLMs doing back and forth, right? We ask them a question, they answer us. And many people in the OpenAI circles And now with a new API from GPT-4o Mini, it became proved that this is what they're doing next. LLMs are going to be more looking like streaming. So streaming means that they're going to be doing what we're doing right now. So Google Meets is doing streaming, right? It's data streaming. So data is going one way and it's going another. That's how we can see each other and talk at the same time through a screen. We're not like asking a question like a message and then receiving an answer as another message, right? That would be the discrete method so far. So we're going to be looking at more and more is LLMs seeing information or going through information in a streaming sense. So looking at a video, for instance, looking at, I don't know if my screen just stopped here. I do think so. Sorry about that. So LLMs are going to be looking at video. They're going to be looking at real-time audio. They're going to also be looking at data streams from all sorts of internet use, and also from robotics. So this is what we're looking about next. As LLMs are more efficient, and these neuromorphic hardware comes up, this is what I think is going to be a trend. Right. So there are still many limitations for LLMs and for transformers in general. One of them is the hallucination problem. So transformers will always hallucinate. Whoever says otherwise is going to be lying. You can actually make the transformer hallucinate very rarely, and make it quite restrained. But so far, it's part of the architecture to hallucinate. Hallucination is just a word that we made to say when an LLM is actually performing exactly as intended, but the results are not matching the real world. And that's the problem just because of how LLMs are working right now. They're working in an artificial world, which is the internet. And in the internet, anything is possible. So all the information can be real or fake. That doesn't matter. A human that would exist in the internet would also have no way of knowing what would be real or not, because everything would exist there, right? If we talk about then robotics or these LLMs working in real world or even working with code, things are going to be different. So I would say that hallucination is going to be tempered with in the long term by making AIs more connected to the real world, and looking at the physics and testing the physics with the real world, and seeing the results and adapting their findings to that, instead of training it in kind of incomplete and apparently arbitrary data that for them it's arbitrary, right? Because it's our expression of the world, right? So that is very much connected to also another limitation, which is the training data set, right? So training data sets are currently done by humans. They're built by people working in Nigeria and in other countries that don't pay a lot of money for their employees. And the companies as OpenAI have been open about it, that they do use these workforces to categorize their data and basically get all the training data set for them. That means they're quite possible that all this data is quite biased, and it is. It's been shown to be biased in the past. Oops, sorry about that. My screen keeps sleeping and keeps going down. All right. But yeah, so that's the problem, limitation on data set. And my assumption is that actually with streaming, that's going to, reduce. But you can still go around it by, doing better RAG and fine tuning it. And then finally, the size. So LLMs are better when they're bigger. They're worse when they're smaller. Seems simple, right? Brains with more neurons are better in a sense, but also not that all the time. Some big brains, like the whale, the blue whale has a much bigger brain than humans, but it's apparently not doing calculus underwater, or as far as we know. And that's because it's not just the amount of neurons that matters, it's also the tuning of all those neurons. Because in big animals, most of the brain power is actually just being used to manage all of the thousands of cells that they have more, or all of the actually millions of cells that they have more than us. So the same applies for neural networks. So LLMs also have this limitation. When we make them very big, they can be much better, but they also become very power hungry and not as efficient. So there's actually an effort of making them smaller and more efficient continuously, which we just saw with, for instance, 4o Mini, right, from OpenAI. It's much smaller than ChatGPT 3 apparently, and much better. It's as good as 4o. Right, and one example here is, for instance, what happened with Llama. So Llama 3.1, which was just released this week, it is 405 billion parameters wide. just as you know, the normal size of other regular LLMs or open source LLMs is usually the 70 billion parameter size, but 405 billion parameters is really big. But it outperforms even ChatGPT 4.0 and Cloud Sonnet in a couple of tasks and a couple of benchmarks, apparently. So open source is actually going after many of these different players here. So, right, I think we kind of already did this one. Right, I wanted to just, before we go, so we just have like 4 minutes. So I'm just gonna go through a couple of the tools, right? So Claude is one of the very interesting ones that I think is very interesting to look at, because not of its capabilities of just thinking, but because of its capabilities of executing. So let's say we wanna have, write me a dashboard that uses AI, or let's just make me as well uses AI for investors to collaborate in a round. Make it psychedelic styled, for instance. So now what it can actually do, which is quite interesting, is that it's not just writing what it should be, it actually is going to actually create it real time. So I think this is one of the key interesting differences, that tools like Claude 315 by themselves, just by writing the code, are interesting, but then you would actually need to know how to execute the code, and most people actually need to do that. But that's ending. So now the it's not really a great one. I really did ask it to be psychedelic in shape, but now we can actually change it. We can say, okay, change the layout, or make it dark mode, or now use this data set, or use that data set, et cetera, et cetera. So that's an interesting one here, which is a very interesting application. It's going to change the way people build applications for sure. Another one here, another type of tool is browsing the web. So Perplexity is one of these tools. And if we go here, we can actually ask it. So it's using ChatGPT in the background, but we can actually ask it to, for instance, go online and search the web for a specific question instead of just, answering what it knows from data. It still makes mistakes though, but it.
For example, João, how many business angels exist in the world?
Right. It's probably going to make a mistake on that one for sure.
Good question, Rui.
Okay. So I didn't use the Pro mode. Pro mode is using a bit more advanced question search. Okay, so it said 300,000 individuals, but better than the number. Let's see what source it used. So this was the source for that quote here.
Yes, this is the number.
All right, so that's correct. That's good.
Yeah, 300,000 Americans, 300,000 in maybe in Europe.
Right. Then Canada has a couple of other regions. Okay. And you could actually write it. Okay, make me a table of that. Let's see if it makes a table. All right. Okay, let's go. So this is pretty good. We're using data from the real world and coming back from the real world and compiling it. Although I must emphasize that every time we do this, we're kind of going into this muddy waters of hallucination. Right. Okay. So 1 minute to go. Then there's elicit. Elicit is interesting for, doing research. So the way we research things. Let's go back to a question I asked in the past. So what's the state of the art of nuclear fusion right now? Right. So it had that index that was so fast, and it's using also GPT-4o mini, so it's super fast these days. But you can see it gave me an answer for a general understanding of what it found on the 4 main papers. They also have it analyzed 8 papers. If we upgrade, it pays them money. But then you can actually see each one of the papers by themselves. You can go to the papers and see a summary for that paper for different base structures, and you can research really in a different speed. And then finally, this is the last one. I'm going to go very soon. I know you guys have busy lives. I'm just going to show you this one. So this is what I think is going to change the way that we use computers, and it's going to be the next trend on operating systems, right? I'm selling a lot here, I know, but I think it's quite powerful. So if you don't know about these guys, they're called Open Interpreter. They're a startup, very interesting one. And what they do is, and I don't recommend you using this right now because it's quite scary, but it runs an LLM on your computer and it has access to all of your files. So I can actually ask it what's in my desktop. And it's using GPT-4 Omni. It's going to run this code that lists what's in the desktop. So there's, all right, it found a couple of things. Never mind. Make me an email drafted talking about a meeting I'm having right now. So this is a big task, right? It's going to actually need to know a lot of different things. So it's actually asking the recipients, etc. I'm going to ask go to my calendar and check my current meeting and add those recipients. Right, so it's actually going to need to execute a couple of code here. And I'm doing it in a safe mode. So as you can see, it's not running the code whenever it wants. I need to say yes, at least for it to run code. Because imagine, it would go into my calendar and go back, get information from all of my events with current date. Then it can, actually is asking for questions that start in the less than 1 hour before, for events that started with the 1 hour before. And it wasn't able. So because we're actually, over the hour, but you can see that where this is going, right? It actually now has the ability also to see the screen and do a couple of other things, but it is quite interesting. So yeah, so in a summary, this is kind of like a high-level state-of-the-art of these tools. I will, of course, say that there's much more stuff here happening. I tried to compress it into an hour, which was not easy at all. But I hope it was helpful for you guys.